So a little bit about me. My name is Marine, and I am a data scientist at Intelinair. Have any of you guys heard about Intelinair? Do you know what we do? Okay, yeah, great. All right, so we are an agtech company. We help farmers make their farming and taking care of the fields more effectively. So we take, basically what we do is we take imagery from satellite or from airplane providers, and we analyze those images different ways. We have both analytic algorithms, which I work on, and we also have machine learning algorithms for different types of problems. We show some different alerts. For example, we might tell the customer that they have a weeded area, they have some waterlogged parts over there, and maybe give them some advice as well on what they can do. I am also a master's student, a second-year master's student at Yerevan State University, majoring in applied statistics and data science. And I am also interested in general operational stuff, DevOps, MLOps, and data engineering as well. All right, so like I said, we mostly work with field imagery. We do image processing, data analysis on that, and the tasks that we solve vary. So we might have some classification tasks where we try to decide whether a field is planted or not, or is emerged or not, and stuff like that. We have segmentation tasks where we try to find out the parts that are weeded, or maybe we want to find the parts that are soil and actually unmanaged, so we don't need to track them, we don't need to calculate them in our statistics and stuff like that. So each of our models in production has its own Dockerized image that gets all of these different types of imageries. You can see the first one over here is just the regular RGB image that is taken. We have the infrared, which is colored here in red. We have thermal and other stuff that I didn't want to show here. We have also topological and other things which are more difficult to process. So basically, if we wanted to infer something on a specific field, we would need to have all of this imagery. We would need to pre-process it to kind of combine and calculate different statistics, indices that are more important for specifically field processing. For example, the last image that you can see here is called an NDVI, which is a vegetation index, and it shows how well the greenery is growing there. So this is something that has significantly more value for the model than using these images separately, for example. So yeah, my main point is that we have one Dockerized image that is running on a GPU instance because it's going to do all of the pre-processing, it's going to do the inference, it's going to do the post-processing, so whether it needs to calculate some probabilities, aggregate results and stuff like that, and then give the result back. So this was working fine, but we had plenty of reasons to change that. First one being the costs that we were paying for the instances. So like I said, our models were running on AWS EC2 instances. The types that we were using were P2 because these are the ones that have GPUs, and high RAM because we needed a lot of memory to pre-process the data that we had. And let's just remember the price for the lowest one, which is 90 cents an hour. Okay, so another problem that we had with these type of instances was the scalability. Because these models are, these types of instances are quite popular, it's often not very convenient, but you won't always have them available, so the scalability was definitely a problem for us. Another thing was for different types of models that we had, they might have some slight differences. Some data sets for training, let's say, would be similar, but the work would be done twice because there was no sharing in between the code. So that's basically my next point, which is duplicated work. And also no versioning, so everything was kind of mixed up. If you wanted to update the data set halfway, that wouldn't be very correlated, so it will be difficult later to find out what you were doing, why you decided to change some stuff. So I think that my main point here is the high costs and the scalability. These are the top ones that made us decide to restructure. And here are the points that we decided to implement for the transition. The star of the show is obviously going to be the Triton server, because that is the new thing that we discovered this year. And I'm also going to talk about the other changes that we added to our production. So the first one I'm going to talk about is the ML service. So what we call ML service actually has three main components: the API, which we are going to use to talk to our database, some Python classes that we implemented to make that job a little bit easier, and the database itself. The first two are not really important, because the first one is just we use the Fast API, which is a web framework to work with databases in Python. It's like a RESTful API in Python. The other classes that we implemented was just for our ease, because we were doing very specific things like uploading a model, registering a data set, making some inferences, and saving their results, which I'm going to talk about in a minute. So that all of that was made much easier with our custom methods, and then the database itself. So we added another database, and we decided to do, I mean, you can store anything you want here for your convenience. This is what we did. Firstly, we registered the data set. So depending on what project you're working on or how you got the data set, you can register it here. You can add some comments, you can add tags, you can remember later how you decided to choose this. And you can also have some versions. So for the example that I brought, where maybe you are training a model and then some time passed and now you would like to update your database and retrain again, the versioning makes it much easier to store and keep track of. The next one are the models and versioning, again, similarly. So when I talk about registering a model, it's going to involve both actually having the model in the database, or writing down that we have this model of this version, which it automatically will keep track of, and also uploading the model to a repository, or maybe you are using an S3, which we are. So we are going, we created a model repo, which is going to have each type of model and its versioning there. Yeah, like I said, to each of these you can add custom tags, comments. For models you can have maybe some configurations and stuff. And the last table that was also very important for us was one where we kept the inference results. Again, similarly, you can keep some metadata here. You can keep some computation times. You can keep some statistics. I don't know, maybe the mean and standard deviation interests you for a particular image that you are processing, for example. And the general inference results, this makes it much easier to keep track of how your model is performing. I have the three most important points right here. So the first one being easy evaluation. So you can just run all of your inferences, store them in a database, and then later, whatever metrics you want to get, you want to calculate some type of different losses, or you want to calculate average metrics, you can, it all becomes just a query and it's dynamic. You can also gather other computational statistics. So in your database, you can keep the inference time. You can keep information about how much of the GPU you are using, how much CPU you are using, how well you are utilizing your resources, basically. And then also track performance. So maybe you have an imbalanced data set, or maybe you have some very specific examples that you are interested in. You can look at how the different versions of the model performed on that specific example. You can visualize that all of this becomes much easier when you have just a database. It becomes much easier to work with. All right. Now let's talk about the Triton Inference Server. So this is an open source serving software that is developed by NVIDIA. And it is basically made to execute and deploy AI models easier mostly on GPU instances, of course. So there are several good things about it. First one being how many things it is supported by. So it supports a bunch of different frameworks. The most popular ones, I guess, being PyTorch, TensorFlow, TensorRT, which is again developed by NVIDIA, and I'm going to talk about later. But it also supports custom backends if you wanted to write something in Python, for example. As for the platform support, I mean, it is mainly developed to be used on GPU instances, but you can also scale it to use on a data center, on edge platforms, cloud. For CPU, it is also it is possible to run it on a CPU-only instance, although it's not recommended because you are probably doing heavy inferences. So this server is going to become basically a REST service where, just like in any REST service, you are going to make calls. In our case, you are going to make post requests to the server, giving it the model name and the data that you want to run the inference on. This is a little bit of the backend, so you can see that the server can manage multiple GPUs. It is really, really optimized, so you can run several different models on the same GPU, for example. You can, it automatically schedules the tasks, so you can also make asynchronous requests to it and then get the results. It does its own health checks. As you will later see, its own client also does its own scaling and load balancing, so it basically takes care of everything. Yeah, I think that's all I wanted to say here. So the way I said previously, our entire Docker image was stored on a GPU-based instance. However, now we can run the entire pre- and post-processing parts, which I'm going to kind of virtually separate on just regular CPU machines because they're not going to use your GPU resources. And then only once the tile, in our case, because we tile the image to process it, once the tile is ready to be passed through the model, you can call the Triton server and it can do the inference and then you can get the result. So yeah, you can see how the resources are optimized here. And then yeah, like I said, the Triton server has its own Python client, which makes everything much easier. It does a load balancing for the request you are sending. It also scales the service if you are making a request and there are no servers running in the servers, it will up a machine. And yeah, it takes care of the backend with the mapping to the IP addresses as well. All right, now for the models and how we would deploy them. So the server is going to have two main types of configurations. The first one being the one that has all of the information about all of the models, which is not very interesting because it only has the model name and the version, so I did not include it here, but that's all it is. It has a model name and the version. Okay, let me take a water break, sorry. Okay, and the second type of configuration, which we are going to need, each model is going to have one of those, and this has a very specific structure. You can find it on their official website in the documentation. It needs to be of this specific format. It needs to have a name. You can add a platform or a backend. The supported ones here are TensorRT, TensorFlow, and Caffe2. And you can have additional information. Some models are harder to work with, so you will need to specify some dimensions. You will need to specify batch size. So there are models that can only work with one, with batch size 1. So you can specify all of that here. And you will need to compile the models in order to use them here. So there is a difference between saving a model and compiling the model. When you compile it, you not only save the state dict, or you don't only pickle the model itself, but you can also add information about the losses, metrics, optimizer that you are using. In PyTorch, you have PyTorch JIT, which takes care of all of that. In Keras, there is Keras compile. And again, developed by NVIDIA, there is TensorRT, which is the fastest one. And we compared JIT with TensorRT, and there was something like a 6-time difference in speed of inference. And there is also a speed difference between just JIT save and PyTorch save, which is interesting. Another thing worth noting is that when you save the model in JIT, it also preserves all of the functionality that the module has at that moment. So for example, if you were to save a model that was developed in PyTorch 1.5 and then try to load it in PyTorch 1.6, but there was some functionality changed, for example, the division is being done differently, maybe there is some type conversion or something like that, it will not load. So it will tell you that something is wrong. Like I said, the Triton server supports TensorRT, TensorFlow, and Caffe2. But an interesting thing is that you can't convert every model to TensorRT straight up. So what we had to do is we had to convert our models to JIT and then compile them into TensorRT, which is also interesting. All right, and lastly, that was, I think, all about the restructuring. And so now what we were able to do because of this is we chose another GPU instance to run our Triton server. You can see these are the G4 instances, and even on their website, they are described as most cost-effective GPU instances for ML inferences and trainings as well. So if you look at the price here, it is now about like 50 cents an hour, but taking into consideration that now this one server is going to be able to serve, in our case, I believe it was up to 4 different inferences, and each GPU can also, so each GPU has a copy of your model if you wanted to utilize that, if you have a bunch of different tasks to do. So we were able to change the instances from P2 to G4. This is only for the Triton server. For the pre and post processing, you can use any other regular instance depending on how much memory you are going to need for your other actions that you are doing. It can be R5, it can be M4, something like that. And as for the resources, so the main resources that you can use is available on the NVIDIA website. They have the official documentation. They have a quick start guide, so you can get started with that from zero. Like I said, it's open source, so the images are available to download. You can, if you wanted to just play around, you could. The official GitHub is also linked here. So if you go to Triton Inference Server, they have both the HTTP client and the servers here. There is one tutorial I found while I was researching, which is again pretty good if you wanted to start from scratch. This is going to help you. And yeah, I would say generally just use their website because they have a bunch of different tutorials. They have specifications about documentations. Also, if you are doing, if you are going to be doing it on AWS, I believe they also have the images there on AWS Marketplace, so that will make your job even easier. Yeah, I think that's all I wanted to say. I would also like to give a special shout out to our engineering team who implemented all of this, and now I am able to talk about it here. Yeah, and that's it. Thank you so much.
Thank you for a great presentation. Did you try another inference servers, for example, TorchSurf for PyTorch models or TF surfing for TensorFlow models, and maybe compare with Triton?
Not really. I mean, we haven't tried TensorFlow because we mainly work with PyTorch. The PyTorch server, I'm not entirely sure if we have tried that. did? Okay.
Thank you.
Yeah, Triton turned out to be the...
Torch is better?
No, Triton was better.
Yeah, thanks for your talk. I'm curious, you've told about the 6x speedup you got from TensorRT. Could you describe the model or the architecture of the model that gains such a speedup for TensorRT?
We mostly use CNNs. I think so we tested regular ResNets, and I think on ResNet 50 we got three times the speed. For the one that had a 6 times speed, maybe it was some type of a UNet.
Okay, great. Thanks.
So what are the possible problems or mistakes that you can face or have faced while doing this?
What do you mean?
While using going to the servers.
Oh, well, while moving to the servers, I mean, initially the kind of concern that we had was moving the data from one instance to another, because previously we were doing everything on just that one instance. There was no data sharing, basically. And in this case, we are passing basically those tiles of data through an API request, but since all of that is done in AWS network, everything is really easy, so you don't really have to worry about that either. Yeah, I would say that was our main concern initially, but we didn't have to worry about that.
Can it take to move from bring your data on everything to that server, like initially?
So for the server specifically, I mean, you aren't really bringing any data to it because the image is ready. All you need to take care of is compiling the models correctly, which is going to be a change that you do code-wise in the way that you work in your production. Everything else is just available to you. Like I said, it's open source, so you have everything available to you, the repos. You only need to add configurations to them. You have the image, which you basically run on an instance. So yeah, upping the server for yourself shouldn't be that difficult. Yeah, I think.
Thanks for the talk. Have you ever worked with the models replacing model in the production by these techniques, or A/B testing when the model is actually using there? When the model is actually there and you have the new version of the trained model for updating, or A/B testing having a different model?
Yeah, so if you are updating a model version, the Triton takes care of that by itself. So you only need to add the configuration. Everything else is done there automatically. So it checks what models are available to it, and then it automatically downloads them if it needs to. It has one specific repo, which I forgot to mention, but Triton needs one specific model repository where all of the models should be kept. The names must match the folders. It needs to have specifically the versions inside them. The model needs to be in one of those 3 formats I mentioned. So all of that is very specific, and otherwise you only need to change the version number in the configuration, and once the Triton gets up again, scales or something like that, it's going to change it automatically and change the model that it's running on the GPU. Thank you.